Hello everyone and welcome to Growing 4.2. Our homework assignment or our ACES assignment for this investigation will be 8 through 13 and 15 and 17. So looking back again at our learning targets for 4.1 and 4.2, we'll begin to understand exponential decay and write equations for the relationships, and I will compare and contrast decay and growth relationships. If we turn to page 62 in our books, brings up problem 4.2 of fighting fleas representing exponential decay. So exponential patterns like the one in problem 4.1 in which a quantity decreases at each stage by a constant factor show exponential decay. Exponential decay, let's go look at our vocabulary. Exponential decay, a pattern of decrease in which each value is found by multiplying the previous value by a constant factor greater than 0 and less than 1. So you can stop the video if you want to read through the example. The factor the quantity is multiplied by at each stage is called the decay factor. We had our growth factor, now we have our decay factor, and that's defined up here as the constant factor that each value in an exponential decay pattern is multiplied by to get the next value. The decay factor is the base in an exponential decay equation and is a number between 0 and 1. Again, you can pause the video to read the rest of that vocabulary. So therefore, now we know a decay factor is always greater than 0 and is less than 1. In our last problem in 4.1, the decay factor was 1/2 because we went from 64 square inches down to 32, down to 16, so on and so forth. Each time we made a cut on the ballots, our area of square inches went decayed in half. So our exponential decay patterns also exponential functions. That's what I want you to be able to explain. If you need to go back and look at the definition of exponential functions from back in Investigation 2, go ahead and do that. Should be in your vocabulary. After an animal receives flea medicine, the medicine breaks down in the animal's bloodstream. With each hour, there is less medicine in the blood. Well, a dog receives a 400 milligram dose of flea medicine. The table and graph show the amount of medicine in the dog's bloodstream each hour for 6 hours after the dose. Okay, so here we have our graph on the left-hand side with the time since the dose. Okay, in 1 hour we've gone from 400 down to 100 as shown in our table over here. So take a look at the pattern that you might be seeing over here. And according to the table, how much medicine was in the dog's blood initially, and then how much remained after 1 hour and after 2 hours. Now that you can kind of see a pattern, how would you describe the pattern of decline in the amount of active medicine in the dog's blood? Okay. Now if we turn to, well, actually let me show you the video real quick.
Well, Mr. Doodle, you've got a case of plaid rash. You probably got it from not wearing enough checks or stripes. The good news is this medicine is very effective. Take 1 pill every 4 hours. In a few days, you should be cured.
Can I just take a pill every 2 hours to speed up the process? It's kind of embarrassing to walk around like this, and I clash with everything.
Don't go overboard with the medication. Your body will metabolize 40% of the medication every hour. So after 1 hour, 60% will still be left in your system. After 2 hours, 36% will be left, and so on. After 4 hours, you'll need another dose.
Okay, Doc, I trust you. But if the medicine breaks down at 40% per hour, how long before the medicine is completely out of my system?
Okay, so that's kind of the decay factor we want to take a look at. Same things going on here. How long is the active medicine? In the last one, in the video, it had a decay rate of 40% per hour. So how much is remaining in each hour, and how long would it take for it to completely leave his system. In this problem, though, with our dog and its fleas, we want to, part A, study the pattern of change in the graph and table as we were talking about before. And then how does the amount of active medicine in the dog's blood change from 1 hour to the next? Write an equation to model the relationship between the number of hours H since the dose is given and the milligrams of active medicine left, or M. So how's this graph similar to the graph we made in problem 4.1, and how is it different? Then does the relationship displayed in the table and graph represent an exponential function? Explain why. Secondly, in part B, we have a different flea medicine, and it breaks down at a different rate. This time 20% per hour means as each hour passes, 20% of the active medicine is used. So we're going to start with 60 milligrams at time 0. That's the rate of decay, is 20%. Initial dose is 60. So we need to extend and complete this table to show the amount of active medicine in the animal's blood at the end of each hour for 6 hours. I've given you a little more information down here. This is how I want you and your teams to be able to complete part B of this question. Again, 4.2 homework is 8 through 13, 15, and 17. So look for patterns for exponential decay, and remember that decay pattern, decay factor has to be between 0 and 1. Good luck, and look forward to your questions in the classroom.